This is lecture 8. Last class we have discussed that what is transfer function, and we started solving one particular problem, that RLC circuit. So today we'll complete that example first. So it is that series RLC circuit. So you have one inductor and you have that capacitor. So that applied voltage is VIS, and output voltage across that capacitor we are interested in to find out. So this is that capacitive reactance and this is inductive reactance. This is that Laplace operator and this is R. So the current flowing through this circuit is IS. So what we are doing, we are just solving this problem in Laplace domain. So I think you know that if you have one inductor, the current flowing through this inductor is IT, and you have applied the voltage Vt across this inductor. Say L is that inductance. Now that Vt equal to L di by dt. So suppose this is current IT. So now if you take that Laplace transform, so it would be Ls Is, say initially relaxed. That means we consider that initial condition is 0. So now Is by Vs, that means if you would like to represent in input output form, so that one is equal to 1 by Ls. Now here one interesting point is that if you want to represent this block in terms of Vs by Is, then that would be equal to Ls. So that means if you go with that input output relationship, if you take that input as current and output as voltage, then you have that transfer function that is Ls, which is improper. And we have already discussed that improper transfer function cannot be realized physically. So whenever you want to realize a circuit comprises of any inductor, so always try to realize that circuit in terms of one proper realization. That means this is the transfer function, and if you look at that numerator degree is 0 and denominator degree is 1. So this is a strictly proper transfer function, and here input is voltage and output is current. So this is actually that proper realization which can be realized physically. So now go back to this particular example, that if you write that KVL, that is R IT plus L di by dt plus 1 by C integration I dt, or you can say that this is tau I tau, so 0 to t. So this is equal to Vi T, that input voltage. So taking Laplace transform, what you get, that is R into IS plus LS IS plus 1 by CS IS equal to VIS. So here, as we are interested in to find the transfer function, so all initial conditions are 0, because from definition of transfer function you have seen, we need to assume that all initial conditions are equal to 0. That is one of the disadvantages of transfer function based modeling. So now here what you can have, that IS, so this is now that algebraic equation, so just manipulate it, that 1 by CS equal to V by IS, then that IS current equal to VIS divided by R plus LS plus 1 by CS. Now what is V0S? So V0S, that output voltage across that capacitor, V0S equal to 1 by CS into current, 1 by CS into IS. So then 1 by CS into IS is here, that is VIS divided by R plus LS plus 1 by CS. So now if you write this particular expression in input output form, so here you can see that this is your output, this is output, and this one is input. So in our input output form, that is V0, that is V0S, so output by input, that one if equal to, if you simplify it, that CS will be cancelled out, so that is 1 by LC square plus RCS plus 1. So this is the transfer function from input to output, and we get it applying that Laplace transform and considering all initial conditions equal to 0. So I hope now it is clear to all of you how to find the transfer function for any physical systems, linear time invariant dynamical systems. Of course, the transfer function modeling based technique only applicable to linear time invariant system, we have already discussed in detail. So now we'll be discussing another framework of modeling, that is called that block diagram representation. So in this course, from the very beginning, you have seen that I have represented dynamical systems in block diagram form, and now we'll be treating this particular subject formally. I'll be showing that the different terminologies and different operations that we can do in block diagram framework. So this is another technique for representing a dynamical systems. So let us see what is that block diagram representation. So far I think we have already discussed and already we have seen how to represent dynamical systems in block diagram form, but here we'll be showing it in detail. That is that block diagram representation. So block diagram representation. The common elements in block diagram of most control systems include comparator, then that block representing individual transfer functions. So let us see that the common elements in block diagram of most control systems include, so these are actually that main block diagrams involved in control systems, closed loop control systems. So those are comparator, then blocks representing individual transfer functions, so I am writing that abbreviated terms, that TF for transfer functions. Which are those? So those are reference sensor, then output sensor, actuator. Already we have seen those blocks, controller and the plant. And the block diagram comprises of various signals. So that first one is that input signal that actually drives that closed loop control system. So input signals, that is that reference command. Then output signals, that measure controlled output, that measure signal. And then the disturbance, noise. So these all are that unwanted signals which are inevitable in closed loop control systems. And another one is that feedback loop. So basically in block diagram we have seen it, and now again we are going to draw. So in block diagram, so we have that comparators and various blocks like reference sensors, output sensor, actuator, controller and plant. And there are many signals like input signals, output signals, disturbance, noise and feedback loops. So let us represent it in block diagram form. So this one is the block diagram of a general control systems. That means that standard control systems. So if we consider a closed loop feedback control system, so what are the standard blocks involved in that into that loop? So we are going to see this. So we have that comparator. So this is that comparator. Normally we represent like this. Here you have that reference sensor. So it is just like a filter. You have that input, that is that reference command, which comes to that comparator, and now this is that feedback loop is coming to this particular point. Now here you have that error signal, and after that you have that controller. So now that controller output is fed to that actuator. So in between that actuator, so again there is one comparator, so in between that actuator and that plant, so disturbance may enter the system. Then you have that plant, and then this is that major output, and here we take that feedback signal, so that is that output sensor, that is that output sensor, and in the feedback path, so noise may enter, and this is that feedback loop. So here suppose this signal is V in, suppose this signal is V in and this is VO, and here you can see that the various blocks involved in a standard closed loop control systems, and this is that general block diagram of a feedback closed loop control system. So there is one important point should be noted down, that is what happens if any nonlinear block is involved in the feedback closed loop control system. That is, in the block diagram that you have seen from this particular diagram, that block diagram basically it is input output representation, and in case of nonlinear system, as that Laplace transfer the transfer function concept does not hold, so in that case we just represent that block in time domain, that is say input ut and say output yt, and g is that nonlinearity. So this is actually represented in time domain, that is time domain. In the time domain, so this is actually for nonlinear block. So this is for the nonlinear block. That means if you want to represent a nonlinear element involved in a closed loop control system by block diagram, So you should go with that time domain representation. The reason is the transfer function concept is not applicable to nonlinear system. But in case of linear time invariant system, a block is represented like this. This is actually that input output behavior. So US is that input and Y is that output, and here you have the transfer function. And of course, so this is that transfer function. So what we do in closed loop control systems, so in case of closed loop control system, if we would like to represent it in block diagram form, so we write that input variable and output variable, input variable and output variable, and inside that block we write the transfer function of that particular subsystem. So now let us discuss in detail, that means the different components involved in that block diagram. The first one is that comparator. The first one is that comparator. It is very simple. That means, just we need to do some algebraic operation. So this is that comparator. This is the symbol, and here two signals are coming to that comparator, and I am just writing it for both. That means in time domain as well as in Laplace domain. That means for linear as well as for nonlinear. Just now we have seen, that means if it is a nonlinear block or nonlinear control systems, in that case, we need to represent it in time domain. So this is that signal, and here you can see that RT is coming plus, and YT you need to subtract from this RT, so that ET equal to RT minus YT, and in Laplace domain that ES equal to RS minus YS. So this is the basic operation takes place in comparator. Similarly, if both signals are added, so suppose RS and here YS, I am not taking that time domain expression here, so it is just same as the first one. So what is ES? So ES equal to RS plus YS. So that means whenever you will be representing that comparator, so which are important, first thing is you need to put that arrow, and another thing is you need to show that whether it is plus or minus. So these two things are important, and also you can take, say, more than one or two signals. Like if you have a comparator like this, and here suppose three signals are entering, so like R1S and here R2S, and suppose this is R3S. So you can see that three signals are entering and one signal should be going out from that comparator, otherwise it does not make sense. ES would be equal to R1S plus R2S plus R3S. So this is actually that basic operation takes place in comparator. These all are the algebraic operations, and this operator, I hope you understand that how to realize it. You can use any op-amp circuit just like adder or subtractor So practically you can just realize this comparator using some op-amp circuits, and these are the different structures of the comparators. That means you can take say positive, so here in this case if you think that this is a part of that feedback, so you can see that this is a positive feedback type things, and here this is a negative type feedback, and here you have considered three signals. And you should not forget, whenever you will be representing a block diagram and one comparator is involved, then of course you should not forget to mention this plus or minus sign, and also you should put that arrowhead. So now we'll see some example. Say if we take a simple closed loop control system, so here you have that comparator, and suppose you have that plant here, and now you can see that this is the plant transfer function GS, and here whenever you close that loop, so this is that feedback path, and the feedback path transfer function is HS. So you may consider that this HS is suppose that sensor transfer function, or you can just put any other filters or any other blocks in the feedback loop whose transfer function is HS. So if we take that negative feedback loop, so this is that output YS, and the reference signal that you have given, that is RS, and so this one is that error signal ES. So now we are interested in to find what is YS output and RS. That means what is the transfer function from this reference signal to output signal, measured output. So how to solve it? So all the signals and everything seen in algebraic form, so just all algebraic operations would take place. So you can see here that ES, that means if you see the comparator here, in case of this comparator, so ES equal to RS minus, so this signal you can see that, okay, so this signal is suppose XS, so RS minus XS, and then this XS is equal to, so here you can see that the output equal to that HS into YS. So now if you replace it here, so you'll get that RS minus HS YS. Then what is YS? So we can see it here that YS equal to GS. Here you just look at here, GS into ES. So now if you just replace here that RS equal to HS, then in place of YS, that is GS ES. So first you have replaced here, and then you have replaced it here. So then if you just simplify it, you bring this right hand term to the left, and you will get that I plus HS GS into ES, I have taken common ES equal to RS. So from here you can see that ES equal to 1 by, So if you take, it is single input single output system just for better understanding, so that's why I'm just removing that I, but it also holds for multi input multi output system. So in that case you need to write this is I, and here you cannot do that division, so basically you need to write that matrix inverse. So ES equal to here 1 plus HS GS into RS. So then what is your YS? You can see here that YS equal to GS into ES. So that is 1 by 1 plus HS GS into RS. So what was our objective? Our objective was to find that YS by RS. So that means YS by RS equal to GS by 1 plus HS GS. So this is the transfer function. This is the transfer function from reference command RS to YS. So now one interesting thing you can notice here, that this is a closed loop control system, and this particular portion of that block diagram is called that forward path, and here this is that feedback path. So now if you have a closed loop block diagram, closed loop control systems like this, whose forward path transfer function is GS and feedback path transfer function is HS, then what is the transfer function from reference input to output? We have derived it here, and you can see that GS divided by 1 plus HSGS. So that means the forward path transfer function divided by 1 plus HS into GS. So HS is that feedback path transfer function into forward path transfer function. So you should remember this particular structure, because whenever you will be simplifying block diagram and your objective is to find the transfer function, every time you need not to do all these derivations. So only just looking at that block diagram you can directly write what is the transfer function. So now we will just see another technique in block diagram representation, which is called that block diagram reduction. Block diagram reduction. So what is block diagram reduction? So suppose you have a part of the block diagram that is US, and here this is YS, and this is called that branching point. So you have that HS, you have that branching point from this particular point. So this is a part of your block diagram. So here you have that signal YS, you have tapped it, this is called that branching point. So this particular block diagram is equivalent to That means if you take the branching point from this point to that point, then what happens? So that means if you change the branching point, here you can see what is the signal coming to this particular point. The signal is coming, say, xs equal to, here you can see that hs gs into us. You can see it here, the signal what is coming to this particular point, that is hs into gs into us. So now if you change this tap point from here, and as these two are equivalent, so at this particular point you must have that same signal. But how can you have it? So you have that us here, so then obviously this block transfer function would be hs into gs. So then you can see it here that xs would be equal to hs gs into us. So then you can say that this particular block diagram and this particular block diagram, they are equivalent. So here what you have seen, that means if you change this branching point position from here to here, then you need to change this block diagram transfer function to keep the same signal here. Then only these two block diagram representation would be equivalent. So let us see the other case. So if you have a block diagram like, so this is gs, now suppose you have that comparator. hs, and so here suppose you have that ys, here you have us, and here you have xs. So then it is clear that this ys equal to gs us plus hs xs. Now if you would like to represent this particular block diagram in equivalent form, so basically what we are trying to do, we are trying to shift this particular comparator from that place to this place. So if we shift that comparator, then we are interested in to see how the block diagram transfer functions would be changing. So here you can see that gs is here, gs, so the same transfer function is here, and then if we change that one, if we change the position of that comparator, you keep it as same here, and then the input what is coming to this block xs. Now if we put hs by gs, then let us see whether they are equivalent or not, because in this case your output ys equal to gs into, so here you have that us, So that is US plus HS by GS into XS. So now if you multiply it, you have that GS US plus GS will be cancelled out here. So that means it is HS into XS. So then you can see from here that this particular expression and this expression, they are same. So that means these two block diagram representations are equivalent, and we can see it here that whenever you change that tapping position, then you can see that the block diagram, the revised one. So here there will be a product, and whenever you change that comparator position from this place to this place, so then there will be one division. So it is very easy to understand just by looking at that final expression. That means the what signal you are getting, and basically you need to make it both the expressions same. Accordingly, you need to modify the block diagram transfer function. So let us solve one example, and here this particular example is under the heading that block diagram reduction. So that block diagram reduction. So basically we'll be applying block diagram reduction technique to find the transfer function. So what is your objective? Your objective is to find the transfer function of that block using block diagram reduction technique. So block diagram reduction technique means you need to follow these techniques. That means shifting that branching point or shifting that the position of the comparator. So let us see a simple example. So the block diagram that we have, so this is that problem given to you, that RS is the input signal, and you have two comparators, and in this particular problem I am just writing G1. So G1 means G1S. I am not writing showing that Laplace variable in the transfer function. So all are the transfer function, rational transfer function. So you have that G3, and you have another comparator here. So in this particular block diagram you can see there are three comparators involved. G4, these all are the transfer function. I am not showing that S. So now this particular block diagram control system has two loops. One is that inner loop, what I am drawing now. So this is the tap position. So it has one inner loop, and this is that outer loop. So what is that objective? So find transfer function from RS to YS applying block diagram, reduction technique. So that means the other technique is that you have done in this particular example. That means you just simplify all the algebraic equations involved in that block diagram and you can find the transfer function. But here what we are trying to do, we'll be applying block diagram reduction technique to solve this particular problem. So we need to find the transfer function from Rs to Ys, Okay, so we'll be showing all the steps. So first you look at here, this particular point here. So if we can change this particular branching point from this point to this point, then you can see that we'll be having one forward path. This is that forward path, and this H1 will be coming into the feedback path. So then directly we can apply this particular transfer function because it will come into this particular structure. So the first simplification is, so you need to show all the steps here. That means this is that block diagram, these are two comparators, and here you have that G1. So now we are just going to change the position of that tapping point. So whenever you will be changing that position of the tapping point, you have seen it. That means if you change the position of the tapping point from here to here, so you'll be having a product. So then you can see it here. So you have G2 into H1. Here you have that G2, then G2 into H1, and the tapping point is now here. And then you have G2 as it is. Then you have that G3, and you have G4. You have that another comparator. So the rest of the part remains same. So rest of the part remains same. So this is plus. Here you have that. Okay, I forget to mention this negative. So it's negative feedback here. So that is plus. So this is that first step. I hope you understand that first step. So basically we have changed that tapping position from here to here. So whenever you change the tapping position, you can see the signal initially it was coming like this. So then if you change the tap position from here to here like this, so then there will be the product. That means G2 into H1 or H1 into G2. This one. We are considering here single input, single output system. So then there is no problem. Just for better understanding, if you have multi-input, multi-output system, then you just follow that it would be H1 into G2. So now you can just look at here that two systems are cascaded. So whenever two systems are cascaded, what happens? Suppose you have that G2 and you have that G3. So whenever two systems are cascaded, you can see here this is XS, this is YS, this is ZS. So then YS equal to G2S into XS, then ZS equal to G3S into YS. So if you replace this YS here, then what will you get? That is G3S into G2S into XS. So that means whenever two systems are cascaded like this, so we can represent it as that is G3 into G2, that is that equivalent one. So here we can simplify this part. That means we can write that G2 into G3. And another thing we can see here, whenever you have suppose G1 here and you have G2 here, so now if your signal is going like this, suppose you have that comparator, this is plus and this is plus. So suppose this is XS, this is YS. So what would be your YS? So YS equal to G1S XS plus G2S into XS. So that means you can write that G1S plus G2S into XS. So in all the block diagrams I am not showing S, so you should not be confused. So here you can see that I write S, but here I have not written S. So basically that is G1 plus G2. So then you can see the structure, and here if you look at the block diagram that you have, so particularly you can see that these two structure, these two block diagrams, this one and that one, they are cascaded. So basically you can simplify that is G3 G2, and then similarly this G1 and G2 and this particular one is connected in parallel, just like this one. So the effectively the total transfer function, effective transfer function would be G1 plus G2. So in this case the transfer function would be G3 plus G3 into G2 plus G4. So let us simplify this one. So now if we draw the block diagram, so you have one comparator here, another comparator here, and you have that G1. So this part I keep as it is, this particular part G1, and in the feedback that is G2 into H1. In the feedback you have G2 into H1, G2 into H1, and this is the tapping point. Here you have the tapping point. So now, as now we have discussed, that means this particular part can be represented as G3 G2 plus G4. So here you have one block, that would be G3 G2 plus G4. So this is that simplified block diagram. So now we'll be concentrating on this particular loop, and you can see here that loop and this loop, they are same. So what is the transfer function from input to output? That is the forward path transfer function, GS, divided by 1 plus the feedback path transfer function and the forward path transfer function. So here if you look at this particular loop, so forward path transfer function is G1 and feedback path transfer function is G2 into H1. So what is the transfer function from this particular point to that point? That would be G1 divided by 1 plus feedback path transfer function, that is G2 H1, into forward path transfer function, that is G1. So it is simple. And so what would be your block diagram? So block diagram is, I am just writing from this particular point to that particular point. So that means you have only one comparator, that is RS, here, only one comparator. Now this point is this point, and now you see from this particular point to that point, the transfer function that I have, that is G1, this transfer function, that is G1 divided by 1 plus, say, G1 G2 into H1. So as they are single input single output, so there is no problem if you write G2 H1 G1 equal to, say, G1 G2 H1, so there is no problem. And so from this particular point to that point, the transfer function is this. So now you can see that rest of the part, that is this particular transfer function, that is G3 G2 plus G4, this one. So now this is that block diagram, and close this particular feedback path, so you have that negative things. So now these two transfer functions, this transfer function and that transfer function, they are cascaded. That means whenever they are cascaded, you know, they will be in product form. So whenever they are cascaded, so then you can write what is the transfer function here. So you have a block, so I am just writing it from this point to that point. The transfer function is G1 into G3 G2 plus G4 divided by 1 plus G1 G2 H1. So this is the transfer function from this particular point to that particular point. So now the rest of the part is that feedback loop and that comparator. So then again we draw the simplified block diagram. That means this is that comparator RS, you have that plus sign, and then you have that feedback path minus. So then what is the transfer function from RS to YS? You can again apply this particular structure that we have done here, this particular structure, that is forward path transfer function divided by 1 plus product of forward path and feedback path transfer function. So here you can see the forward path transfer function that you have, this is the transfer function. Then what is YS by RS? So YS by RS equal to the forward path transfer function, that is G1 into G3 G2 plus G4 divided by 1 plus G1 G2 H1 whole divided by, because this is forward path transfer function, you can see it here, should not be confused. So the forward path transfer function is that GS, then whole divided by 1 plus feedback path transfer function into forward path transfer function. So that is 1 plus feedback path transfer function here, this is 1, so that is 1 into the forward path transfer function, that is g1 g3 g2 plus g4 divided by 1 plus g1 g2 h1. So now if you simplify that one, you will get that g1 into g3 g2 plus g4 1 plus g1 g2 h1 plus g1 g3 g2 plus g1 g4. So this is ys by rs. So this is the transfer functions that you have, and if you simplify this particular block diagram, so finally you can draw that this is that block diagram representation. So this is that rs, and you have that ys, and inside it you have the transfer function g2 plus g4 into 1 plus g1 g2 h1 plus g1 g3 g2 plus g1 into g4. So now you can see that the transfer function that we have obtained just by applying that model, the transfer function reduction technique. So today what we have done, so we have solved one simple example and we have derived what is the transfer function for that series RLC circuit. Then we have learned some terminologies of block diagram representations, that is that comparators, and these are actually not the terminologies, these are some important blocks involved in that block diagram representation. And this is that closed loop transfer function, and we have seen what are the important blocks involved in that closed loop feedback closed loop control system. Then for nonlinear system, that is important, that means we need to write that present that block diagram in time domain, and in case of LTI system we can do it in time domain as well as in Laplace domain. So the comparator, we have seen the basic algebraic operations that take place in case of comparator, and then we have seen the block diagram reduction technique. So there are some methods we have followed, and finally we have solved one example. Thank you.